Howdy Bobcats, thanks for viewing my video. Wanted to go a little bit into standard enthalpies of formation. Hopefully you've been reading about it in the book. Just go over some of the details here. A very kind of cool thing you can use for finding the amount of energy takes to produce or is given off in a chemical reaction. So when we're looking at these reactions, we have to use this, we have to be under certain conditions. There has to be constant pressure, so the pressure isn't changing. And then we use a calorimeter to find that out. And sometimes it's not very easy. There was an example of graphite changing graphite into diamond that I did not get a chance to do, but graphite and diamond both have the same chemical formula. They're both just made out of pure carbon. Here's a diagram of it here. And if you look at this picture here, they look different, they take on different shapes. Here's a diamond with the carbon molecules. Here's the graphite. Graphite is these sheets. Which one of these would be more stable? The graphite is actually more stable, right? Stuff you use in your pencil. More stable than diamond. And the reason is that the carbon molecules, if you look at them, are farther apart. The nuclei of the atoms are farther apart than they are in diamond. And so diamond will actually eventually decompose or change into graphite. The way you can use it in a pencil, even though it's more stable than diamond, is these sheets, and so they have these layers that are in the graphite pencils, and so you're rubbing these layers off. They get then stuck on the paper. Here's just some different forms of carbon. This is Buckminster fullerene. It's kind of cool. Here's a carbon nanotube, kind of interesting. I don't know much about these other ones, but these are what is called these are iso, same chemical formula, different structure. I forget the name of them off the top of my head, but anyway, back to the standard enthalpies. So that's an example, graphite to diamond. Now we're looking at these reactions. Some other things you got to think about is that sometimes it's hard to measure these directly, and that's why we can use this. And really what it comes down to is that a molecule that is produced, that is made, no matter how you get to that, either combining elements to make it or decomposing something to make it, right? It's that concept we were talking about last class of the state function. Okay, it's a good example of that state function and why we can use this. It's kind of cool and interesting, though. Now, let's talk about this. It's time for standard enthalpies of formation. Here is the symbol. Okay, so you have enthalpy, standard enthalpy, that delta H still. Okay, of formation, you have this F, and so these molecules get formed from their elemental compounds. Okay, the degree symbol, it doesn't mean temperature. What it means is that this has been gotten to by using the conditions of standard conditions. Okay, we haven't talked too much about this, but it's a little bit different than STP, standard temperature and pressure. And we'll see what those exact stipulations are here. Abbreviated SS sometimes. If they have a compound, those standard states, if it's gaseous, has to be under pressure of 1 atmosphere. Okay, if it's liquid or solid, it has to be in a pure substance, right? So it's not a mixture; it's pure molecule, or if it's in, it could be aqueous, right? If it's aqueous, it has to be in the concentration of 1 molar. Remember, molar is moles per liter, that moles per volume. Okay, for elemental, it is 25 degrees Celsius, so different than standard temperature and pressure, which is 0. And when you have an element, it's in the state of matter that is on the periodic table. That's what it's given by. Okay, all elemental, whatever an element exists as naturally, those we kind of is our starting point. And so the enthalpy of formation, standard enthalpy of formation for all elements is 0. 0 kilojoules usually what we measure it in. Okay, just a heads up if you get into deeper some chemistry, the International Professional Association of Chemists, the one that make the periodic tables and stuff, they use a different standard of pressure. They use 100,000 pascals. It's a little different than the 1 atm. Hopefully we can get into some gas laws so we can learn more about that. Okay, so let's look at the formation of nitrogen dioxide from its element. We have elemental nitrogen plus elemental oxygen being synthesized to make nitrogen dioxide. Okay, and we can measure the amount of energy it takes to make this as 34 kilojoules. Okay, that's the standard enthalpy of formation, how much energy it takes, notice the positive, to make nitrogen dioxide. Okay, here's another example. Oh, and of course, remember it has the half there because these are always given of the 1 mole of what we're looking for, 1 mole of this product. Okay, so we can have to, if we balance this, we have to make this 1, we have to use this as a fraction. It's the same thing though. Here's methanol. It's made from 3 different elements, right? And so here's the standard. Notice it gives off, it's exothermic, gives off negative 239 kilojoules for every 1 mole, right? So this is per mole. So that's why this has to be 1 mole here. So we can just use this energy, okay? Now, essentially every molecule has a different value, okay? And so you have to use your textbook. If you look at the back, there's Appendix 4. It has almost every molecule and the standard enthalpy of formation, okay? So what we can do is we can take that and figure out what, from this reaction, how much energy it would be either given off if it's negative, exothermic, or how much it takes you have to put in if it's positive. Okay, so here's what's actually happening, right? You have, say we have methane plus oxygen. Here's the combustion of methane. What you're looking at here is this kind of pathway. It's kind of a cool way to see this. You have your reactants, you have your methane, you have your 2 moles of oxygen, okay? And one way you can look at it is breaking up into its elements, okay? And then forming the products from this elemental. We looked at this last unit with the excuse me, with the Hess's law, right? But the way we can figure this out is everything is made from elemental, okay? Even these reactants were formed from elements, and so we have to break these bonds to form these, right? So we know, and so we can look at how much energy that takes, and then to form these bonds, how much energy is given off, okay? So we can think about it like that. I'm going to go right to the equation here. Let me just read this to you. The enthalpy change for a given reaction can be calculated by subtracting the enthalpies of formation of the reactants, okay? And so here's our equation. The change in the enthalpy of the reaction, okay, at standard state, there's our degree sign there, is we're going to subtract the enthalpies of formation of the reactants from the enthalpies of formation of the products. I think this got deleted here. Of the products, okay? And we also have to multiply by the number of moles that are in here, okay? And so if we look at this equation here, it looks really big and complex and scary, but it's pretty cool. This, of course, just like in math, this is the sum of, right? So we're going to add up all of the enthalpies of formation for all the products. We're going to add those all up after we multiply by the number of moles in the reaction, okay? And then once we get that answer, that number, we're going to subtract the sum, right? The sum of all of the heat of enthalpy of formation for all of the reactants, okay? Multiplying them all by the number of moles, okay? It's kind of cool. So there's your equation. I'll come back to refer to it a couple times, but it's the math is pretty easy. You're just going to multiply, going to get that products, add them all together, and then do the same thing for the reactants and subtract it from the products. Okay, so here's an example. Here is the reaction of carbon monoxide plus water to yield hydrogen gas and carbon dioxide gas. Okay, one thing you got to really pay attention to when you're doing these is that state of matter, because it is different. It'll have, if you look at that, I would turn to that page, back of the appendix 4 there. I'd look at that right now, and I'll probably upload it for people that don't have a textbook, so you can look at it. Okay, and so if we look at that, carbon monoxide has a heat of fusion. A heat of enthalpy of formation of negative 110.5 kilojoules. Okay, for water, at the gaseous form, it is a negative 242. I'm not going to put the unit here. For hydrogen gas, because this is elemental, this is the elemental form, this is 0. This is our starting point of how we can, this is kind of our baseline of how we form everything. It's from elemental. It's how we measure it. It's where we come up with these numbers. And for the carbon dioxide, it's negative 393.5. You could probably find these online if you looked them up as well. Okay, and so remember, what we're going to do is we're going to sum all of the heat of fusions of formation, right, of the moles times the products, okay, multiplying by the moles. This will be the products. Don't get confused. These are the reactants, these are the products, okay? And then we're going to subtract the sum of all of the, same thing, of all the reactants. Oops. I wrote that wrong. The mole should be on the other side, but it doesn't really matter. Okay, so this is going to be 110. There are no moles. In all of these problems, the moles are just 1, so we're going to keep them. 110, that's my time here, 0.5 plus negative, don't forget this, that's biggest thing is making those mistakes. And here we're going to have the negative 393.5, okay? And so you can do it all in one thing here. Negative 393.5 minus, put these added together, negative 110.5 plus negative 242. 41. And so the amount of energy that takes, and it was negative, right? Check that. I think negative 395. Yeah. Negative kilojoules.